Okay, so today we'll introduce the concept of momentum. And before I get into the slides, I'll go over one equation, and everything pretty much in the chapter is based on that equation. Okay, so if you understand that equation, then you'll be all set. Okay? Everything will make sense. Okay, so momentum, which is the title of the chapter, is a vector quantity. It's denoted by P, and it's a vector, so you put an arrow on top. And it is the mass of an object times its velocity. So the faster you're going, the greater your momentum. The more massive you are, the greater your momentum. So for instance, a school bus going at 80 miles an hour versus a car going at an 80 miles an hour, the school bus will have more momentum. Okay? All right. Now, I don't know if you guys remember. Do you guys remember Newton's second law? Anybody remember Newton's second law? You might, if I write it down, you'll know it. You might just not know the name. F equal to ma. Okay? So Newton said force acting on an object is the mass times its acceleration. In fact, he actually stated it like this. Force is change in momentum. Okay, this delta sign means change in momentum divided by the time over which that change happens. Okay. All right, so the change in momentum means just change means the quantity at a final point, mv final minus mv initial divided by delta t. Okay, so F equal to m v final minus v initial divided by delta t. So this is the equation we want. This is the equation that most of the chapter is based on. Okay, almost all of the chapter. Okay, so now let's look at the applications. Okay. All right. So the first application, I'll show you the application, and then we'll go into the slides. Okay. If you're in a situation and you don't want to get hurt, what you want to do is you want the forces acting on you to be as small as possible, right? All right, so let me show you a situation. All right, so let's say this guy's driving at 80 miles an hour. Yeah. So the car is going at 80 miles an hour. And a wall suddenly jumps up in front of the car and stops the car. Okay? So the car is stopped. What is happening to you inside? At what speed were you going? You're going at 80 miles an hour too. Okay? And if the steering wheel stops you, okay, so there's the equation. Yep. So there's the equation. So let me write this equation down. F equal to m times v final minus v initial divided by delta t. Okay, so what you want to do, you need to be stopped. This is 80 miles per hour. You need to be stopped. So this is going to 0. Okay, and so this is large. And if you get stopped very fast, if this delta t is small, you get stopped very fast, then the force on you is large. So if you don't want to get hurt and you want the forces to be small on you, what is it that you need to do? You need to stop you over a long time. The longer the stopping time, the smaller the force and the smaller the damage to. Okay? And that's the idea of this thing. So that's what this airbag does. Okay? So this airbag stops you over a larger distance over a larger time. and so you get hurt less. Did you guys understand that? Okay, so that's what the job of a seat belt and an airbag is to do, to increase your stopping time. Okay? And here's another thing that the airbag does. Okay, so let's see. Let's say I'm pushing with my thumb with a force of 15 pounds on my palm. Does that hurt? No. I'll do the same thing with this thing. 15 pounds with a pen. That hurts. What was the difference? It's the same force.
Smaller surface area?
Smaller area, okay? So the pressure is force divided by area. Greater pressures also cause damage. Okay, look at what this airbag is doing. It's applying a smaller force, but it's applying over a larger area as well. So it's doing two things. Okay, the airbag is increasing the stopping time and also applying that smaller force over a larger area. Okay. All right, so you guys understand that? So that's one application of the force. One application of that equation that we'll study. Okay. Here's another application. Okay, let's say you're playing a sport. Okay. So here's that equation. Again, I'll write it down. F equal to m v final minus v initial divided by delta t. And now what I'm going to do is I'm going to multiply this over there. Okay. F delta t equal to okay. So what this is saying is you're applying a force, and this is the time over which you're applying the force. Okay. And that is equal to mass times final velocity minus mass times initial velocity. So let's say you're playing golf. What is the initial velocity of the golf ball? That's 0. It's sitting on the tee. Okay. Now, if you want to make millions of dollars, what is it that you want to do? You want to launch that ball as fast as possible. So you need to apply this, make this as large as possible. Okay. So here's how the club applies the force. Okay. So this is okay. So this is the force on the ball before the club comes in contact with the ball, and then as the club comes in contact with the ball compresses, and the force increases. It peaks to about 2,000–3,000 times the weight of the ball, and then goes back to 0. Okay. This F delta T, it's essentially this area. Okay. And it is called the impulse. It's this area. So larger that area, okay, and we'll write it as average delta T. Larger that area, faster that ball will fly off. Okay. And so this is called impulse. Okay. So we'll look at that. So now let me write this down. So 1 okay. So one of the applications is if you increase the stopping time, you're decreasing the force. That was one application. The second application was you want to increase the impulse if you increase that, then final velocity will be large. You'll be launching something with a great speed. That's what happens in sport. Okay, when you want to kick a soccer ball and stuff like that, you apply a large impulse. Okay, so initially the ball will be at rest, and when you apply a large impulse, then the ball will take off with a great speed. Okay, the third application that we'll look at, you see, it's the same equation, and you see you're seeing different aspects of the same equation. Okay. Okay. Okay, now let's see. What if F is 0? Okay, if you apply a 0 force on the object, okay, the only way this can be 0, delta t is not 0, so the numerator has to be 0. Okay, so if this is 0, then this has to be 0. Okay, so what we'll see is when the external force is 0, then mv final equal to mv initial. Okay, this is momentum conservation. Okay, so what we'll see is in collisions, before the objects collide, the momentum of the object after the collision is equal to the collision before the collision. Okay, or in explosions, that's also true, and this is the principle on which rockets function. So let me go to the rocket example. So these are the 3 examples we'll see, but let me go to the rocket example. Okay. Actually, rather than the rocket, let me show you the squid example. Okay, so we'll look at this example. So what we're looking at is when there's no force acting on the system, then final momentum is equal to initial momentum. That is mv final equal. Yeah. All right, so here's a squid. Yeah. It has this pouch or whatever. It's called a mantle where it can store water. Okay. Now here's a squid that is at rest. So its momentum is 0. Its initial momentum is 0. Okay. And then I don't know if a shark comes by and wants to eat the squid. And what does the squid want to do? Of course, it wants to run away. And how does the squid survive? It needs to run away faster than the shark. Okay? So here's how it gets away. What it does is squirts out this water. Okay, you'll see in the problem, we'll see this is about 100 grams of water. 100 grams of water is hi there, hello there. How much is your soda? Is that 350 ml or 500 ml? 500. Okay, so can you hold up your bottle? That's about 100 ml. That's how much water the squid squirts out. It squirts out at 150 miles an hour underwater. And the squid takes off. Okay, it recoils. So this momentum, this is the final momentum. The momentum of this water and the squid is 0, the total momentum. Okay, so the momentum of the water, velocity of the water, plus momentum of the squid, plus velocity of the squid is 0. Okay, this is conservation of momentum principle. Okay, so this principle is, why is it called conservation? Because before the event, which is the event is the squirting of the water, the momentum is 0, and after squirting of the water, the total momentum is 0. Okay. All right, so that's how the squid escapes. So those are the 3 applications we'll see. Okay, so the first application is you want to one of the applications is if you increase the stopping time, the forces on you are small. When you want to when you want to get an object to go fast, when you want to change the velocity of an object substantially, then you apply a large impulse. Okay? And when the external force acting on the object is 0, then the momentum is conserved. Okay? P final is equal to P initial. All right, so those are the applications we'll see in this chapter. Okay. So let's get into the slides. Okay. So here's that statement. Momentum along with energy and angular momentum are conserved. Okay. So when external forces acting on the object are 0, momentum is conserved. Okay, that's the statement. Conservation laws place a limit on what an organism can do. Okay? Motion and other behaviors that violate conservation laws simply cannot occur. So you cannot do anything that violates conservation laws. Okay? So conservation of momentum allows us to analyze situations that otherwise would be extremely difficult to understand. So what this statement is saying, so we'll talk about conservation of angular momentum as well, but here's a, okay. So you guys have seen this. Here's a ice skater spinning, okay? And when she brings her arms and legs in, what happens? You guys have seen this on TV. She's spinning and then spins faster, okay? So this is a conservation of angular momentum. Angular momentum is moment of inertia. This is moment of inertia, and this is angular velocity, okay? So this is her angular momentum before, in the initial state, and this is her angular momentum in the final state. Okay. So she's spinning faster. This is angular velocity. This is greater. This has increased. So this must have decreased. Okay. So angular momentum denoted by L is I times omega. I is moment of inertia. Okay, and so moment of inertia depends on how your mass is distributed about the axis. The further out your mass is from the axis, the greater the moment of inertia. So in this configuration, the moment of inertia is decreased, this decreases, and so your angular velocity increases. Okay, so this phenomenon can be explained using this conservation law. It would be very hard to explain using any other laws, okay, Newton's laws and stuff like that. So that's what we mean by that. Okay, so this is a conservation of angular momentum. Moment of inertia decreases and angular velocity increases. In fact, world-class skaters can increase their angular speed by a factor of 5. So they can spin 5 times faster from the starting angular velocity. Okay, so they're able to reduce their moment of inertia by a factor of 5. Yeah. Okay, so an ice skater using arm, okay, so it would be extremely difficult to understand that kind of phenomenon without using conservation laws, okay? And an octopus or a squid using jet propulsion to flee from predators. So you saw that this octopus will squirt out water and propel forward, yeah? And so its momentum is conserved. Initially it was at rest, and then it'll squirt out water and suddenly have a great velocity, okay? An octopus propels itself by squirting a jet of water in the opposite direction. The total momentum of the octopus in the water is conserved. So, okay. Here are two bighorn sheep head buttoning, okay? And they don't get concussions. They go at it at full speed. They hit hard. You hear the noise, and they're not wearing helmets, and they're not getting concussions. So what's going on? Okay, so again, this time we're using this fact. Okay, so to not get concussions, you want to minimize the forces, so you have to somehow increase the stopping time. You increase the stopping time, this will be smaller. Okay, and the way they do that is their skulls have smart, spongy palates, and then on top of that, they have these tufts of hair. So that is what, it's like a cushion, okay? It's like an airbag, and that's what lengthens the collision time and decreases the, they got built-in football, the best kind, okay? Woodpeckers have to deal with that too. Yeah. So woodpeckers, I mean, when they hit, they're pecking on trees and stuff like that. The forces can be very, very large, almost 1,200 newtons, which is twice your body weight. And so they don't get concussions because their brains are smaller, so, among other things. Okay. So nature finds solutions to these problems. Okay. Yeah. So the rams butt head at high speeds. Thick skulls and a spongy cover protect their brains during these high impact collisions. Here, when you're playing a sport, what is your goal? To launch that ball as fast as possible. Okay? And so here, now what you want to do is you want to make this as large as possible. And this is called an impulse. Okay, so initially the ball was at rest, and if you want to make this as large as possible, this needs to be large. Okay. This guy called the impulse is so the force that the club exerts, force as a function of time, is like this. It goes like that. Okay, so the force is 0 before the club is come in contact with the ball, and as it compresses the ball, the force is greater, and this peak force can, in most sports, it can be up to 2,000 times the weight of the ball, and then goes back to 0. Okay, this area is impulse. Okay. And larger the impulse, greater the speed with which the ball takes off. Okay. In sports, we cause a sudden change in velocity. So you're causing a sudden change in velocity from 0 to 100 miles an hour pretty fast. For example, okay, a collision is a short duration interaction between two objects. So a collision is a short duration interaction. The collision between a golf ball and a club may seem instantaneous to you, but high-speed photography reveals that the side of the ball is significantly flattened during compression. Okay, so here's what's happening. Okay, so now this is showing you motion, but when the club comes in contact with the ball, it flattens it, and then as it leaves, the club regains its shape. Okay, so this in sport, the duration of the collision depends on the material from which the ball is made. Harder the ball, shorter the collision. Okay. 1 to 10 milliseconds are typical. So for a golf ball and a club, the collision time is half a millisecond. That's half a millisecond. Baseball and bat, it's 1 millisecond. Okay. Soccer ball, it's 10 milliseconds. A soccer ball is much softer, and I guess that's 10 milliseconds. When two steel balls collide, the collision is 0.2 milliseconds, or 200 microseconds. Okay. So again, harder the objects, shorter the collision time. Okay. So again, so when the club comes in contact, here's the force is 0, and then the force will rise to peak value and then go back to 0. And when we gave you these times, this time for the golf club and ball is half a millisecond. For a baseball bat, that's 1 millisecond. Okay? And for a soccer ball, that's 10 milliseconds. Okay? So that's what that is. Okay, so here's what happens when the ball is compressed. The ball is it's an elastic object. What do we mean by an elastic object? If you apply a force, it'll compress or whatever. And when the force is removed, it'll go back to its original shape. Okay? And you want that. You can't play soccer. If you kick the soccer ball, if it didn't go back to its original shape, you can only kick it once. Okay? In a baseball or golf ball, you want to use the same ball for the entire round, hopefully, right? All right, so it's an elastic object, and it'll regain its shape much like a spring. What happens at the indeed, that's exactly what happens at the microscopic level. Molecular bonds compress. Okay, so the way this thing compressed is the intermolecular bonds compressed, storing elastic energy, and then expand as the object rebounds. Okay. Okay, when you apply a force like this, that is fast changing, that doesn't live too long, that is called an impulsive force. Okay, and this is the kind of forces you apply in sporting events. This is the kind of forces that come into play when collisions happen and so on. Okay, so an impulsive force is a force that doesn't live too long and it's fast changing. Okay, so an impulsive force rapidly changes with time. The forces of a collision are usually very large in comparison to other forces exerted on the object. So what we're trying to say here is the following. So here's golf. So when the club is exerting a force on the ball, there's weight of the ball and there's friction and all that. But the force that the club exerts, so I'm going to draw this. So here's the ball on the tee. There's the weight of the ball, there's the normal force, there's friction force, but the force that the club exerts is so much larger than any other force that this is the only force we need to talk about. Okay? And that's an impulsive force. Okay. So the forces of a collision are very large in comparison to any other force exerted on the object. So this shows how a typical impulsive force behaves, rapidly growing to a maximum, then decreasing back to zero. So here's momentum. Momentum is a vector denoted by P. That's mass times the velocity. And the units of momentum are kilograms, meters per second. Kilograms and meters per second. Yeah. Okay, so the impulse momentum theorem, which I've already introduced. So let's say this is a club exerting a force on a golf ball. And again, the force is like that. The force changes like this. For a golf ball, the collision lasts about half a millisecond. Okay, and this area is called the impulse. Okay, so the impulse is denoted by I or J, depending on the book you use. So we'll use I. So that's the area. The area is impulse. Yeah. And that is this. Okay. So oftentimes it's very hard to measure this force in detail, and we don't care to measure the force in detail. What we'll do is talk about an average force. Okay. And this average force is such that the average force times the time of collision, this area is equal to that area. Okay, so that's what's written here. Average force times the time of the collision is equal to change in momentum, final momentum minus initial momentum. Okay, so if you want to launch the golf ball, so this is 0. If you want to launch the golf ball as fast as possible, then you want a greater and greater impulse. Okay? So the greater the impulse, meaning greater this area, greater the launch speed. Okay? So the only difference between Tiger Woods and me is Tiger Woods he has an impulse 3 times greater than my impulse. Okay? Well, here's an application in biology. Okay, so average force times time equal to mv final. Okay, so let's say this frog wants to jump as high as possible. Okay. So if you want to jump as high as possible, then you want to launch off as fast as possible, right? Okay, now all muscles there's a certain maximum force they can exert. So this is limited. So if you want to, and this is 0, so there's a maximum force that you can apply using a muscle. So if you want to go as fast as possible, if you want to jump high, what can you do? You want to make this bigger. This is fixed. All you can do is increase this time, the time over which the force is applied. So here, you've done this subconsciously. You knew this equation. See, if you want to jump low, what do? That's what you did. When you want to jump high, what did you do? See, you increase that time. Okay. So animals that want to jump high, okay, so they have long legs. So they're unfolding their legs as they're jumping. Okay. A frog making a jump wants to gain as much momentum as possible before leaving the ground. This means that it wants the greatest impulse delivered. It wants this to be large, so this can be large. Okay, this is 0. There's a maximum force that the muscle can exert. Hence, to impart greater impulse, the time over which the force acts must increase. So this must increase. So the time interval during which the force is exerted can be greatly increased by having long legs that can push against the ground for a longer time. Okay? So many animals are good jumpers and have long legs. So frogs have long legs. Any other animals you can think of? Kangaroos, they can jump high, and their rear legs are much longer, and so on. All right. Here's a rocket. The rocket, so, works on the principle of external force acting on it is 0. This is 0, and so momentum is conserved, meaning final momentum is equal to okay, so if this is 0, the numerator has to be 0, and final momentum is equal to initial momentum. So let's consider a rocket in space. This is at rest, okay, so, and there's no force acting on it. So if it wants to go forward, what it has to do is it has to expel hot gases backward. Okay? And so here's the amazing thing. So it can keep speeding up by expelling all these gases. Okay? And the total momentum of all of this will be equal to 0, which was the initial momentum. Okay? And so, again, and you can imagine doing this. So let's say you're on a frozen lake, and bless you. And if you want to go in this direction, what you have to do is you got to throw physics books in that direction, and you can recoil in the other direction. You got to use physics books. All right. So that's how rockets work. Okay, so here's another application. You guys might have seen this game. Okay, you're tossing eggs, and the winners are the person who catches the team that is furthest and catching the egg without breaking it. So let's look at the equation. How do you not break an egg? By applying a small force, the smallest force. So if you want this to be small, well, you got to stop the egg, which is the same. You want to make this as large as possible. The stopping time as large as possible. How do you make the stopping time as large as possible? When you're catching, you bring your hands inward, and that's why you're making stopping time, okay, as large as possible. So, but if you want to make an omelet in your hands, just hold your hands still, and you'll have a broken egg. So, the winning strategy is to pull your hands inward towards your body while catching the egg, so that it slows down over the longest possible time. Thus, the force exerted on the egg is the smallest. You saw that that's the job of the airbag as well. Airbags plus seat belts together, they increase your stopping time, decreasing the forces on you. Okay? And in addition, The airbag spreads the force over a larger area. Okay? So the bighorn sheep, they have thin, flexible bones in their sinus cavities. Okay, so the bones are like springs. Okay, so they can increase stopping time. They have spongy mass between a double wall cranium, and that also helps, I guess, in shock absorption. The brain comes to rest in roughly 0.25 seconds. Okay, so that's a long stopping time. Remember, the golf ball is so this is 25 milliseconds. Okay. The golf ball collision is 1 millisecond, so this is an enormous time. Okay. The impact, while dramatic, are not forceful enough to cause any brain injury. Okay. So that's why they go at it. Okay. So here's an airbag. So this is a this is a hedgehog, and the spine's protected from predators, but it's also used for another thing. Okay, these guys can fall from trees and not hurt themselves. Okay, when they fall from trees, what they do is they roll themselves into a ball. Okay, and then this thing acts like an airbag. The spines act like an airbag. Its thick spines cushion the blow by increasing the time it takes for the animals to come to rest, thus decreasing the stopping forces. It's increasing the stopping time. Indeed, hedgehogs have been observed to fall out of trees on purpose to get to the ground faster. Okay. So when you have an airbag, you might as well use it, right? So, and I'm sure teenage hedgehogs just climb up the tree just to fall down, right? So now we'll look at the conservation of momentum. Okay, so here's Newton's second law, and that net force is change in momentum divided by time. Net force is external forces plus internal forces. So let's say when two objects are colliding, these are the internal forces, and they're always equal and opposite, so they'll always add up to zero. So this will always be zero. So this amounts to external force is equal to change in momentum divided by time over which that happens. And so if there's no external force acting, then this has to be zero. Change in momentum has to be zero. Okay, that means P final minus P initial equal to zero. That means P final equal to P initial. So that's what happens in collision. Here's the initial momentum, the sum of these two momenta, and the final momenta is the momenta of these two guys. Okay, so this must equal that. If this is zero, this must be zero as well. Okay. That's what happens for a rocket. If it's at rest, its momentum is zero, and then the way it takes off, it expels hot gases. So, okay, if a rocket is at rest, if it wants to take off, it must expel hot gases. Okay, and the more gases it exports, it exhausts, and faster it exhausts, the greater its speed. Okay. So most rockets, they're heaviest. So what happened, if you want to accelerate, the burn time has to be large. Okay. So when the space shuttle was on the launch pad, it was burning 12,000 kgs a second. 12,000 kgs is 12 small cars a second. That's right. Its thrust was 7 million pounds. Okay, so when a rocket is on a launch pad, if it weighs 100 pounds, it's exerting a thrust of about 150 pounds. You got to exert a thrust greater than your weight. and you're heaviest when you're on the launch pad. All right, so here we'll show you momentum conservation. Okay, so just a little problem. Okay, so here are two objects colliding, and what happens is they stick together and go as one after the collision. So the momentum after the collision should equal the momentum before the collision, because okay, so the momentum after the collision should equal the momentum before the collision. Okay, and what this car is mass m and this car is mass 2m, and then they collide. Okay, so let's say the initial speed of this guy is v initial, the subscript I saying initial. This is at rest. So the initial momentum is mvi, the momentum of this guy, plus the momentum of this guy, which is 0. And the final momentum is the two guys have stuck together, so the total mass is 3m, and there's the final velocity. That's the final velocity of this guy. Okay, so this should equal this. mvi should equal 3mvf. The m cancels, so vf is 1/3 vi. So here's, I just did a bunch of math, but I want to tell you what's amazing about this. Okay, this is just a momentum conservation principle. That is, the momentum before the collision is equal to momentum after the collision. Okay, and if they stick together, the final velocity has to be, so in this situation, when this is twice the mass of this, okay, so when this guy's twice the mass of this, see, the final velocity is 1/3 the initial velocity. If this was going at 30 miles an hour, this is going at 10 miles an hour. If this is going at 90 miles an hour, this is going at 30 miles an hour. Did I tell you what the material is made of? No. If they stick together, their velocity is 1/3. Okay? You can't violate conservation laws. Okay? So that tells you exactly the speed at which it's going. So that's what the lawyers in accidents do. You know, the expert witnesses and all that. They tell you in an accident only this can happen. Okay? If somebody claims that they're going at 200 miles an hour and hit you and stuff like that, they can do a precise calculation and tell you if somebody hits you at 200 miles an hour, what will happen. So here's the squid that we talked about. Again, this is momentum conservation. Final momentum should equal the initial momentum. Okay, here's a squid. Squid rely on jet propulsion, so squids are rockets. Okay. When a rapid escape is necessary, a 1.5 kg squid, 1.5 kg is about 3 pounds, 3.5 pounds. Okay. So a squid is about 3.5 pounds. At rest has 100 grams of water in its mantle. So it's got that much water in its mantle, about 1/3 of a can of soda. And so that's in store. And when it wants to escape, it squirts out this water. And it squirts out this water at 45 meters per second. 45 meters per second is, like I said, about 130 miles an hour. Here's the amazing part. 130 miles an hour, you're pushing water in water. How fast does a fastball baseball? 100 miles an hour. You're throwing a baseball in air, and all you can do is 100 miles an hour.
It's like a sneeze.
Yeah. A sneeze is 100 miles an hour? Okay. So that, look at that. So all you're doing is pushing air in air. That's easy. You're pushing water in water much harder. And you're pushing it at 130 miles an hour. Imagine the amount of energy it takes, right? You don't do this unless you have to run away from a shark. Okay? So it pushes it out at like 140 miles an hour, and then it'll recoil. Okay, so, and here's the calculation. So the initial momentum is 0, and that should equal the final momentum. Here's the mass of the squid times the velocity of the squid, mass of the water times the velocity of the water. So mass of the squid, velocity of the squid, plus mass of the water, mass of the water times velocity of the water should equal 0. Mass of the squid is 1.5 kg. Velocity of the squid is what we are calculating. Mass of the water is 0.1 kg. And velocity of the water, it's in the opposite direction. So we call it, this velocity is positive, this velocity is negative. Bless you. So this is negative 45 meters per second, equal to 0. And so the velocity of the squid works out to 3 meters per second. Yeah. All right, let me do the calculation. So what we'll do is, this times that is 4.5. I'll bring it to the right. So that is 1.5 times velocity of the squid is 4.5. And velocity of the squid is 4.5 divided by 1.5, which is 3 meters per second. So the squid goes off at 3 meters per second. Usain Bolt runs at 10 meters per second. Okay, so this is 1/3 his speed. Okay, so the squid takes off at 3 meters per second. Of course, the drag on the water will slow it down. Okay? But hopefully that's enough to get away, escape from the danger. Yep.
And they're kind of shaped like a bullet, so.
I'm sorry?
They're kind of shaped like a bullet. So
Right, yeah. Yeah, so, yeah, you gotta be aerodynamic and stuff like that. So here's another example of that, of momentum conservation. Okay, here is uranium. Yeah, let me pull up. Okay, there's uranium. What that 92 number means is it has 92 protons. And the 238 number is the mass number. That tells you, so, well, it's got isotopes, but uranium-238 tells you how many protons and neutrons it has. Okay? So that's what this number is. Okay, so here's uranium-238. It has 92 protons, and 238 minus 92 is 146 neutrons. Okay? Anyway, so here's a uranium that is at rest. So its initial momentum is 0. Okay? Now this will radioactively decay, meaning it'll radioactively automatically split into 2 pieces. And here's a smaller piece, and here's a bigger piece. Okay? Now here's the deal. See, the momentum was 0, so the final momentum has to be 0. So these 2 pieces, so here's the thing, they have to go exactly in opposite direction. They can't go in any other direction. So if this was the piece, the 2 pieces can go in any direction, but they're always exactly opposite to each other, because the final momentum has to be 0 as well. All right, in addition, their speeds have to be related. So here's the small fragment, its speed was measured to be this. Okay, so the small fragment speed is that, and the big fragment speed is that. Okay, so the big fragment is going almost 100 times slower than the small fragment. Okay, and their speed is such that the final momentum has to be 0. So because the initial momentum is 0, the final momentum has to be 0. So the mass of the big fragment times its speed minus 2.5 times 10 to the 5 plus the mass of the small fragment times its speed should add up to 0. Okay? And in addition, the mass of the big fragment plus the mass of the small fragment should equal 238 units, which was the mass of the, which was the starting mass. Okay, so between these two equations, see, you have two unknowns, the mass of the big fragment and the mass of the small fragments. So if you have two equations and two unknowns, you can solve for them. Okay. And so it turns out that so this goes through the calculation, and the mass of the big fragment is 234 units, and the mass of the small fragment is 4 units. 234 plus 4 is 238. Okay. So when it splits up into these two pieces. And so you see, just from momentum conservation, we were able to calculate the masses of the two pieces. Okay. So that's what momentum conservation allows you to do. You can calculate the two masses. However, we don't know the chemical, we don't know what element this is. And to find out what element that is, you have to do chemical analysis, okay? Because different isotopes can have the same mass. So you really have to ultimately do chemical analysis to find out. And when you do the chemical analysis, you find that the big piece is a thorium nucleus, okay? So the uranium nucleus splits into a thorium nucleus and a helium nucleus, which is called an alpha particle. Okay? So again, when this guy splits, these two guys have to go exactly in the opposite direction, okay? And their momentum is 0 if the momentum of this guy is 0. Okay? So that's what momentum conservation lets you do. Okay? Now we'll talk about angular momentum. Okay? So just like P is linear momentum. So this is when you're traveling in straight lines and so on. And angular momentum is when you're spinning. And angular momentum is a vector as well. So angular momentum is the moment of inertia times the angular velocity. So when you're spinning, okay? This is conserved as well, okay? So the torque acting on an object, this is the external torque, is equal to change in angular momentum divided by the time over which that change happens. Now it turns out that in nature, okay, external torques are 0. Okay, so often, when you're applying random forces, in many situations, external torques are 0, so this has to be 0. Angular momentum does not change. Okay, angular momentum is conserved. So final angular momentum is initial angular momentum. So if there is no external torque acting on a system, the angular momentum of the system is conserved. So if this is 0, then this will be conserved. Okay, so that's what happens in hurricanes. This is just like a spinning skater. Okay, what happens is, as if an air mass, so here the I is a low pressure area and the pressure is higher here. So high pressure drives air masses towards the low pressure area. Okay, and as the spinning hurricane, as the air mass comes closer, just like a skater that spins faster. So the air is moving fastest around here. Okay? As air masses from the slowly rotating outer zones, air masses from the outer zone of a hurricane are drawn toward the low pressure center, their moment of inertia about the center decreases. This decreases, and so that increases. And so the air mass is spinning faster near the eye. Okay? So that's where you get the highest wind speed. Because the angular momentum of these air masses is conserved, their speed must increase as they approach the center. Same thing for a ice skater. Okay? When she spins, when she brings her arms and legs in, she's decreasing her moment of inertia and her angular momentum is increasing. Okay? And like I said, world-class skaters can increase their angular speed by a factor of 5. Okay? So if we're spinning at, initially they're spinning at 3 revolutions per minute, they can get it to 15 revolutions per minute. Okay? So here's a diver. Okay, now you might have seen competition like this. So the diver will jump off from the board. And then in some competitions, you have to spin 3 times and go in the water. And sometimes you only have to do 2 spins and go into the water. So how do you do that? Okay, so here's what happens. So when you're jumping off from the platform, okay, so you push yourself. Here's your body weight. Here's the force you exert. Okay, so if you want to jump off, then this force has to be greater than your body weight. So that's what you when you jump off, you're leaning forward. And in addition, so it gives you an upward impulse, and in addition, it gives you an angular momentum. If you calculate the torque about the center of gravity, this force is making you spin. So it gives you angular momentum. Okay, so when you push off, you give you angular momentum. And once you're in the air, the only force acting on you is gravity. Once you're in the air, only force acting on you is gravity. And there is no torque about the center of mass. So once you jump off, you have so much angular momentum, let's say 10 units, and that angular momentum is constant till you hit the water. So this guy is constant. It's not changing through the entire motion. Okay, well, this guy is equal to her moment of inertia times her angular speed. So if you want to spin faster, all you have to do is tuck yourself in. Reduce this and you'll spin faster. And when you don't want to spin fast, you untuck yourself, increase this. So if you have to do 3 spins, 3 turns, then you tuck yourself for a longer time, you do the spin, and then when you want to stop spinning, you untuck yourself. So by the way, when she hits water, she's still turning. Okay, so she's got to time it perfectly so she appears like she's going straight in the water. Okay? But she's still turning. Okay. So that's what happens. So again, through the entire motion, her angular momentum is constant. I just made up the number, by the way. Okay. As the diver pushes off, the upward normal force from the diving board is larger than her weight. Since the diver is angled forward during the push-off, the normal force exerts a torque about her center of mass. So about her center of mass, it's spinning her. Consequently, she rises and begins to rotate about her center of gravity. Initially, the diver's rotation speed is quite small. However, going into a tuck position, so let's say again 10 equal to. So, however, going into a tuck position decreases this, significantly decreases the moment of inertia, and her angular velocity increases. So when you go into the tuck position, you decrease that and you increase that. The faster spin allows her to complete how many ever rotations you want during her time in the air. Okay. And then when you're ready to go into the water, you untuck yourself and you increase that and you decrease that. Okay. Divers are still rotating as they enter water, and it's very easy if their timing isn't perfect to over-rotate and not enter vertically. Not only do you lose points, it hurts. All right, so it's a double whammy. All right, guys, so that finishes this chapter.